I'll talk a little bit about the MOOS framework. It's finite element-based nonlinear equation system solving framework. And the work we are really still in the middle of doing, which is adding Bayesian inference capabilities and invariant event sampling capabilities. So we're really actively working on that. But yeah, let me see what we already have. Okay, so yeah, first of all, a little introduction into MOOS, the Multiphysics Object-Oriented Simulation environment. It's a DOE-sponsored finite element, finite volume-based modeling framework. I've already heard people say that finite element is kind of boring. Everybody knows how that works, so got me a little discouraged here. Anyway, I'm from Idaho National Lab. It's one of the large Department of Energy multi-program labs. We're basically the lead lab for civil power type nuclear energy use, so not the one that goes boom. And we're sitting here in the Rocky Mountains in beautiful Idaho. It's not a small lab, 5,700 employees. So as I said, a large part of our work is reactor modeling and everything that goes with that. And that is a strongly multiphysics problem. So reactors are inherently nonlinear, multi-scale, and multiphysics problems. We have neutron transport, heat conduction, solid mechanics, fluid flow, material degradation on small length scales, chemistry corrosion. And if you want to do any sort of predictive modeling, you require multiphysics. So arguments. So, hopefully licensing of advanced reactors, if those will materialize, will rely heavily on multiphysics modeling and simulation, because experiments are just really, really expensive in this area. And we require uncertainty analysis, accident scenarios, transients, refueling, material selection. And especially that uncertainty analysis is I think, an important point. I'm personally have been more active on the Mesoscale, and there are plenty of interesting materials microstructure problems when it comes to nuclear reactors, like irradiated fuel, percolation of fission gas bubbles, cracking, hydride formation in cladding materials, etc. And those require all kinds of physical phenomena to model. You have the mechanics, chemistry, heat conduction. For some applications, not particularly in the reactor area, but in other application areas of the MOOS framework, electricity and magnetism are also relevant. And that just means you have to solve a ton of partial differential equations on whatever domains. And for that we developed the MOOS framework, which is, as I mentioned, a finite element multiphysics framework. And the key here is it's supposed to simplify the development of advanced numerical applications and provides a high-level interface to sophisticated nonlinear solvers, and that's where all the math is buried, I guess, and massively parallel computing capability. Although in the context of this workshop, I probably have to put parentheses on the massively. It's parallel. All right, so the whole thing is open source. You can go to moosframework.inl.gov or to GitHub. It is by now really a multi-lab approach. We started it at INL, but we've got substantial contributions from Argonne for reactor meshing and new solid mechanics capabilities, from Los Alamos, and even from Oak Ridge, our good friends at Oak Ridge. All right, so MOOS is used across the world to solve problems just by virtue of being open source. That helped distribution quite a bit. So we have physics modules that we're distributing along with the framework that allow people to use it to solve phase field, solid mechanics, heat conduction, and so on and so on. Fracture, porous flow, reactive transport, geomechanics. So it goes really across large length scales, or from small to large length scales. Here from micrometers to miles or kilometers, whatever your preferred unit of measurement is. Worth mentioning is that there's a huge development effort and a big community around MOOS. MOOS is on a very active development on GitHub, so it's a transparent development process. We have hundreds of Git forks. We have hundreds of unique cloners every 2-week interval. I don't know, GitHub gives me that weird statistics that way. Like 1,100 stars on GitHub, which is apparently really important. We have thousands of issues already closed and pull requests merged. An active user community with discussions hosted on GitHub, discussions with hundreds of participants, unique visitors every day, and lots and lots of contributions. And there's a highly cited paper in Software X for Moose. And yeah, we kind of aspire to maybe at someday be the lamps of finite element modeling, right? Even though that's a really tough or high bar to clear. We do a lot of testing and continuous integration. We have like a public website that shows our testing farm. We run 10,000 tests approximately for every pull request across various parallelization schemes, mesh modes, automatic differentiation options, compilers, operating systems, CPU architectures. We test documentation and code coverage. So we have like several cabinets of HPC computing just for the continuous integration, including several tiers of testing for pull requests and then merging development code into production code. We test over 50 internal and external apps, and we're going on 3,000 cores just for doing CI, like non-stop. And yeah, we can test your app if you choose to develop an app using the Moose framework. We can register your repository and pull it into our CI. And whenever we make a change to the Moose framework, if we break your app, we'll immediately see it, and we can even supply a pull request to you. All right, so Moose is the framework itself, and we base applications on this framework for the various different physics areas. So we have the Bayesian application for nuclear fuel performance. So it models how the thermomechanics of fuel pins, for example, evolve, contact and cladding deformation. We have the Grizzly code for structural mechanics. So Bayesian was basically the first application that kind of triggered the development of Moose. We have Griffin for deterministic time-dependent radiation transport. Pronghorn for medium fidelity fluid dynamics. It's based on finite volumes. Marmot for mesoscale, heat pipe simulation. Those are external applications from other groups and labs. The citations are down here. It's being used at University of Illinois for soft robotics modeling, vascular networks, solid-state electrolytes, geomechanics. It's a big application in Australia where they use it to simulate rock mechanics for coal mining. And yeah, frontal polymerization, I think it was also maybe in Illinois. All right, so just a very quick tutorial-like slide here. Moose framework means Moose is not an application, but a framework. So we provide a C++ infrastructure to write your own physics, basically in PDE weak forms, and then we have like the machinery to apply everything to the mesh and do the assembly, do the solve, do on-the-fly post-processing, yada yada, and everything is done in a really parallel agnostic way. So if you're implementing any physics, you don't have to worry about parallelism in like 99% of the cases. And we have this kind of pretty looking input file format that allows you to configure your simulation at runtime, so you never have to compile in stuff. I'm not going to go into too much detail, just give you a quick glance at what code would look like. So this is implementation of like a term of a partial differential equation. So you have like this advection term here. You create a weak form for that by multiplying with a test function, integrating, and then basically as you read this weak function, that's how you write the code here, test times variable times gradient of the other variable, and then you put that in the code and plunk that in your input file, and you can run a simulation. There's a little bit of boilerplate to allow users to specify configuration options and so on. So let me talk a little bit about mesoscale material modeling. For that, so the framework comes with a bunch of physics modules so that you don't have to implement like all the basic PDEs, right? So there's a lot of stuff is already there, like the fusion equation and for example, stress divergence and everything that goes around it in the so-called tensor mechanics module. So we can deal with small and finite and incremental and total strain formulations, support eigenstrains, eigenstresses, creep, plasticity, like J2 crystal plasticity, and like whatever other plasticity formulations, and fracture using XFEM or phase field fracture, and yeah, and this whole thing is fully couplable in like one big equation system to, for example, a phase field simulation or heat conduction. Right? We have things like strain periodicity, so you can like model representative volume elements. Here you have like grain boundary fracture, and here you have like grain growth driven by elastic energy or strain energy. And then there's the phase field module. I already heard from a couple of people they don't like phase field modeling. They're very skeptic because it doesn't handle fluctuations and nucleation, for example. I had to, yeah. Anyway, I have a slide on that. So that provides the tools to develop parallel phase field codes using finite elements. I have all the base classes for solving Hilliard-Allen-Kahn equations, multi-phase models, KKS1 potential, grain growth models, and we have a system for nucleation. Just some cool-looking examples. This is a grain growth simulation, 6,000 grains in 3D, using an order parameter remapping mechanism. So you can see those grains are changing color here. That's because we're only using like 10 or 15 order parameters to map onto the grains. So not every grain has its own order parameter, but if two grains are far apart, you can like reuse order parameters and dynamically remap them. This is a simulation of 150 million degrees of freedom on 580 CPU cores. This is like a simulation looking at percolation or fission gas coverage on grain boundaries from my colleague Larry Agason. And this is a simulation I made a while ago on studying the formation of void lattices in materials due to anisotropic interstitial diffusion, and those voids, yeah, simply order themselves in this lattice structure, and this ALE type laser melting simulation with heat transport ablation and Navier-Stokes for a project on additive manufacturing.
Are those voids caused by gas bubbles?
Yeah, in this case, we're inserting them preferentially, the vacancies, right? But later in the project, yeah, we went to gas bubbles to stabilize them. All right, so I had a project on simulating radiation and radiation coupled with microstructure. So in a previous life, I worked on developing a binary collision Monte Carlo code and was looking, can we couple this to a finite element-based phase field? And that's just as an illustration for the flexibility of the MOSE framework. Yes, we can. So you can wrap other codes in a way that you can run them concurrent with MOSE. So what we're seeing here is an immiscible model alloy, like an AB alloy could be copper silver, for example, right? If we just heat this up, it'll simply phase separate, right? So just a spinodal decomposition here. That's the simulated FFT, which is also like a built-in capability. However, if we at the very same time run binary collision to do atom displacements, ballistic mixing, basically we get this steady state length scale, right? That does not change, and it doesn't matter whether you start from the mixed alloy or whether you start from the phase separated alloy. You're going toward this like stable dynamic equilibrium, and that has been experimentally observed and also modeled with Monte Carlo simulation. In our phase diagram here, the phase diagram is a function of miscibility gap and displacement driving force, like really nicely reproduces the KMC results. All right. So we're very interested in coupling to thermodynamic database data. So in order not to just do AB alloys or just good-looking pictures with phase field, but something that is based on thermodynamic data. There's a whole bunch of approaches here for coupling, and I'll talk about two. Problem with thermodynamic databases is twofold. Either they are closed, so you need to kind of get the data out somehow and fit a surrogate model. That's not ideal, but we can do that. Or if you have an open database, and there's in the nuclear community, there are databases like TAFID, for example, which have thermodynamic potentials for nuclear systems, uranium, zirconium. We have databases for molten salts, etc. We can get those equations out that describe the free energy surfaces, but we had a problem with the compound energy formalism, where a phase can have multiple sublattices with separate concentrations, and I'll talk about that in a second. So in the first case, you can generate a surrogate model easily by fitting basically, or training a neural net on the free energy, and this is basically the universal function approximation theorem that tells you that you can approximate anything with a neural network, and so we implemented. So we trained with PyTorch and then implemented the evaluation of the neural network in Moose, and that allows us to, in this case, train to a really simple energy where we have the analytical expression. And the reason I'm bringing this up here was what came up when Aidan had his talk. You need to train here on gradients as well, in addition to the energies, because otherwise you get these good-looking fits, which really, if you look closely, have tons of wiggles. And then if you do your common tangents, you get a really screwed up phase diagram. But anyway, so if you do that, you can compare the analytical and then the fitted energy, and this is basically a proof of concept. The difference here is like decimal points to the side, and you get really a good evolution of the microstructure that is almost indistinguishable from analytical free energy. All right, the other thing was the multiple sublattices. So I developed a new phase field model for that. You can take the Kim-Kim-Suzuki phase field model, which has per phase concentration variables that you're solving for, and basically using a Lagrange multiplier approach can change that into a model where you have multiple concentration variables that describe the occupation of the individual sublattices in the individual phases. And now you can suddenly take the analytical expression from the thermodynamic database and directly solve a phase field model with that. So there's a publication from 2 years ago. And let me see, I don't want to go too much into the details. The trick here is that you still need to be able to get the chemical potential with respect to the phase concentrations out of this solve. But that totally works. So the blue points here are the free energy for, I think, delta uranium zirconium phase that has 3 or 4 sublattices. And we can plot the free energy with a thermodynamic solver software, PyCalFat in this case. And what you see up here are all the configurations where the concentration is not distributed across the sublattices in a way that minimizes the free energy, that the real free energy of the system is actually the infimum here. And that's exactly, if we put the phase field model into Moose, and that's what we get as the free energy from this sublattice Kim-Kim-Suzuki model. All right, and practical applications are, as I mentioned, the uranium zirconium phase, which you can form when you have nuclear fuel coming in contact with cladding. And this just works nicely here. This multi-sublattice phase can form nucleate here at the interface and evolve while absorbing the zirconium. Okay, and you can do that with more complicated systems as well. Molybdenum, nickel, rhenium, high temperature nickel alloy that has 5 sublattices on the sigma phase. As a ternary phase diagram here, and we can start phase field simulation somewhere in an immiscibility gap, and those are the trajectory that the system takes as it phase separates, in this case here into 3 phases, or here into 2 phases. So the symbols and the lines are taken from MOOS simulations, whereas the underlying phase diagram is done with PyCalpha, and there's like really good agreement. We really end up where we should on the phase diagram here. Okay, so yeah, I didn't originally want to talk about it, and I see Vasily is not in the audience, so I can maybe even skip. Anyway, so rightly, people have remarked that, yeah, phase field does not intrinsically have the capability to capture fluctuations and model nucleation events, but those are actually pretty important. And what I've developed for that is this explicit nucleation scheme, where we modify the free energy density to cause nuclei to appear, and that works by basically calculating a probability map for a nucleation event to happen, and that can be based on classical nucleation theory or heterogeneous nucleation probabilities, right? Unfortunately, it doesn't come from the phase field, but you have to put it on top of it. And actually, this is not a big drawback, because for the real engineering type applications that we want to model, we could not get the right nucleation rates from phase field anyways, because our samples are dirty. Nuclear fuel is never single crystalline, has defects, has impurities from burnup, et cetera, et cetera. So we're better off fitting to some experimental data here. Yeah, and the trick here is that we add this free energy penalty that penalizes concentrations that are not at my nucleating particle concentration, right? And that gives me a driving force to make the particle appear. And as it appears here, as a copper concentration, this penalty term just completely disappears. And at some point in time, we don't enforce it anymore at all. So this is like a ternary alloy iron copper nickel that forms these neat core shell structures. Yeah, and the neat thing is this completely conserves conservation. We're not explicitly moving mass around here. All right. Okay, and we know where we insert nuclei, so we can pre-refine the mesh, and we can deal with the time steps. So we know that small particles with high curvature have very fast evolution, so we cut the time steps so that we capture the physics. And this upper limit for the time step here, we can also calculate that by keeping the probability to have 2 or more nucleation events happening during one time step at a very small epsilon, okay? And that allows us to deal with that. Okay, so how could MOOS utilize exascale computing resources? So let's talk about MOOS's scalability here. MOOS runs on CPUs. Yeah, that's unfortunately how it is. Hyper, like one of the available nonlinear solvers, does have GPU support, but I mean, that would now come with lots of data transfers. So in practice, we're not really using that. We are currently working with the MFAM team to on a path forward that will allow MOOS to use MFAM as an optional backend to run the finite element assembly on the GPU, right? Ultimately would be very much like a LAMMPS path, where we would now have two little worlds of CPU kernels, GPU kernels, and I'm not super excited about that. Anyway, we can scale up reasonably, so we've run on tens of thousands of cores. Yeah, scaling. We do domain decomposition with Hilbert curve-based partitioning. Communication could hit us, but ultimately scalability of the nonlinear solvers is really what we need to worry about. All right, so let me talk about one important aspect of MOOS, so-called multi-app system. And I think somebody else mentioned that my code is basically just a Fortran function that I call with an MPI communicator. It was like 2 days ago, maybe, it doesn't matter. Anyway, so we can do similar things. So our code is basically a C++ class that we can instantiate, and we can instantiate multiple of those, and applications can instantiate new applications in like a tree-like structure, right? And that enables us to, let's say, do an engineering scale mechanics simulation, and at individual points in space, like do a little bit of mesoscale modeling, see whether you see coarsening of some structural alloy or whatever. So yeah, so macroscale simulations can embed microstructure simulations, and we can have arbitrary levels of solves. And yeah, everything is spread out in parallel to make the most efficient use. Everything, yeah, that allows you to, for example, tie together different teams' codes. And we can have this so-called Moose-wrapped apps, where we wrap arbitrary third-party codes, for example, NEC 5000 from Idaho National Labs, high-fidelity fluid code, map that and make it look like a Moose application, and use the projection and transfer system and the multi-app system, and run arbitrary physics on top of NEC 5000 using Picard iteration, for example. And the other application I'll talk about a little later is, of course, sampling. We can have a main application drive statistical sampling and launch like many sub-apps. And why is this? Why are we not just using a Python script to do all that? You might ask, because we might want to launch hundreds of millions of sub-applications, and this scheme here does everything in memory. So nothing is ever written to disk. Yeah, and in particular, we can every Moose code can be fully snapshotted in memory to a given state, can be advanced and then rewound to the previously saved state. And we can, without writing any intermediate files, we can transmit data up and down the chain, and even among sibling applications since earlier this year. All right, so design goals versus Exascale. Yeah, I think our design philosophy is that user time is really precious. Developer research and analysts are users here. So there's a need for versatile simulation tools that have easy to implement physics and are hardware agnostic. Moose can run on your laptop or on an HPC system. Okay, this is just useless soapboxing. Nobody's doing exascale computing yet. I think you know that. And people keep saying everybody has to do GPUs. I'm not like 1,000% convinced. Yeah, Frontier is basically all GPUs and just a little bit of CPUs. Fugaku was mentioned this morning, I think. It's almost exaflop. Only CPUs, and this upcoming El Capitan computer does use accelerators, but they look kind of different than your uncle's GPU, the AMD Milan 300, which are zero copy architectures, right? So they access the same memory space. So you gotta think a little different again on how you code up your algorithms, right? Because data transfer between CPU and GPU suddenly doesn't matter anymore, which I'm really excited about. All right, so how could we use parallelizing? Yeah, that's hard. It's hard to get good strong scaling, which is important for extended time scales. It's not always easy to get good weak scaling, as we heard with all the electronic structure talks. I mean, some people have succeeded, but yeah, certainly didn't sound easy. That's required for extended length scales. But how about improving accuracy or confidence? So we can work on improving accuracy using multi-scale modeling, where we use this multi-apps approach, because it's expensive to run many high-fidelity or lower length scale models. And we can improve confidence through uncertainty quantification with stochastic methods. Again, that will use this multi-apps feature in Moose. And the route that we're going right now is with Markov chain Monte Carlo as the gold standard for uncertainty quantification, and that's very expensive. What else do I have here? Oh, yeah. Something that I think I may have mentioned in the abstract, but since it's so new, I haven't put it in the talk, is the ability to do active learning. We do have some fresh code in Moose for on-the-fly training of Gaussian processes, where, again, we launch lower length scale or high-fidelity models to train a Gaussian network. And we have a decision class that determines is the uncertainty high or low. Can we use the Gaussian process result, or do we need to add one more data point to the Gaussian process? So that's in Moose, but it's again extremely extremely bleeding edge for us, not for everyone. Okay, so let me give you one example for the failure probability analysis. I'm good. Analysis. So those are TRISO particles. I don't know if you've heard about those. Those are little kernels of fuel surrounded with pyrolytic carbon and silicon carbide, and sometimes an outer pyrolytic carbon layer. They're like a millimeter big, tiny little beads. The idea here is that you encapsulate the nasty fuel in some impenetrable shell that will never let out any badness. Anyway, so there are several reactor concepts that build on that: molten salt reactors, liquid metal reactors, gas-cooled reactors, and usually you don't just shovel these pebbles into the reactor directly, but you encase them in yet more graphite, these TRISO fuel pebbles, or in something that looks like a fuel element, like 12 millimeter across, basically like one of those Rice Krispie treats or whatever, radioactive Rice Krispie treats. All right, so we can use the multi-app system, where we have like a driver application in Moose that does Monte Carlo sampling of various parameters of those TRISO fuel particles. So we know what the diameter and thicknesses and asphericities and so on of those particles should be, and they have certain standard deviations, and we can just sample from normal distributions. This is a slightly older project by my colleague Wen Zhang. And yeah, basically the Moose application runs Bayesian to do in his case, a 1D simulation of such a TRISO particle. You can assume this is like spherically symmetric. We account for the asphericity by like augmenting the stress in a clever way. And then we check for, while we run this 1D TRISO run over many days, weeks, months, or whatever, we can like check, will we get cracking in the pyrolytic carbon layer, will we get the failure of the silicon carbide layer, and so on and so forth. And and then we report back, did the particle fail or not, and compute statistics. So he did 2D simulations of aspherical particles to see how the asphericity drops the failure threshold, and then did 100 million 1D samples on 7,600 cores on INL HPC. It took a day or two. And you get a statistical, or you get a distribution of failing particles, and you can plot this distribution with respect to the particle parameters like silicon carbide thickness, pyrolytic carbon thickness, outer pyrolytic carbon thickness. What we plotted here is solid, the distribution of failed particles versus the distribution of all particles. So basically that failed distribution is unsurprisingly maybe shifted to smaller silicon carbide thicknesses, but maybe a little surprisingly to higher inner pyrolytic carbon thicknesses, and the outer pyrolytic carbon doesn't really have a big effect. Yeah, and you can use that information to, or I guess in the first step, you can use the multi-app algorithm to simulate now a TRISO fuel compact. So this is like this slug of graphitic material, pyrolytic carbon, with all those TRISO particles embedded. And we can run 1D simulations for the thermal transport and the and the neutronics for all these TRISO particles, and every TRISO particle is a little heat source in this compact. And then we have a homogenized approach for the master or main application. And yeah, again, one big main application for the thermal transport and hundreds and thousands of the TRISO particle simulations. And that has two-way coupling. So to get thermal feedback on the particles. And my colleague, that was again Wen Zhang and Yifeng Che, my colleague Yifeng Che, she did this for a microreactor geometry here. There's a lot more to the simulation than I can say in a minute, but again, this is over 100,000 particles, two-way coupling, and yeah. You can get the thermal distribution, species distribution. So this is a TRISO pebble with, again, lots of TRISO particles in it. With the failure probability that we've calculated earlier, we know that there is a couple of TRISO particles that would have failed in this particle. So in addition to calculating the temperature by taking like every particle as a little heat source, we can also take it as a cesium source, which is like the most problematic element that we can have diffusing out, and then we can calculate the cesium transport for this particle. And so this doesn't yet do the failure analysis on the fly, but nowadays this would be a possibility as well. And then you get the two-way coupling with the temperature distribution from the larger length scale simulation. So there are definitely exascale opportunities here for the failure probability distribution. If we have more CPU power, we can easily use that to have our lower scale models, not just one-dimensional, but two-dimensional, three-dimensional, which would enable us to discover more and capture more failure mechanisms, such as properly capturing asphericity and crack formation. We do already have a more advanced sampling method than just Metropolis Monte Carlo. We have parallel subset sampling, where we automatically detect intermediate failure thresholds and only propagate Markov chains that advance us towards a failure threshold, and that can radically reduce the number of samples needed. And for multi-scale coupling, again, you can have higher fidelity, lower scale models and on-the-fly particle failure calculation. Also, we are currently working under an LDRD on surrogate model support with active learning. Again, this would help speeding up because you can replace many high-fidelity model evaluation with surrogate evaluations. Okay, so Bayesian inference, state of practice in computational model validation, at least that's what it used to be in our house, was you have a model with some inputs, and then you look at experimental data and like shift your parameters around, you fit it until you match it, and you have a forward prediction. But what are the input parameter uncertainties here, and how do we take into account experimental data uncertainty? How can we get an uncertainty on the model predictions, and how do we deal with limited experimental data? Actually, I should just cross that out. Never mind about that, and it's not. Okay, here we go. Okay, and so the answer is using Bayes' theorem, which basically by sampling a likelihood distribution, likelihood of observing the data, the experimental data with given model inputs, we can transform a prior distribution of the input parameters, which could be like a good guess or the result of a previous inference step, right? Into a posterior distribution, basically a probability distribution for the individual model parameters. And that likelihood is fairly simple. So have the difference between experimental value and model prediction, and you have to do that for all your experimental data. So that means you have to do a lot of model evaluations, right, to calculate that difference. And you have to somehow sample the likelihood, which is not trivial, but we can do that with Metropolis chain Monte Carlo or Metropolis-Hastings, right? So that allows us to sample probability distributions that we only know up to a constant, right? Because normalizing these probability distributions in very high dimensional space is often not feasible. Anyway, so standard Metropolis-Hastings basically proposes like takes a walk or takes a jump, proposes a new location in parameter space, and then computes likelihood, transition probability matrix, and allows us to sample the space that way. That's great, but that means we have to do all those model evaluations in serial. I mean, we can parallelize over the set of experimental data that we have, but that's about it, right? So we've implemented a parallel Metropolis-Hastings method where instead of taking one trial step, we take n trial steps, and this n can be like up to 1,000. So that allows us to massively parallelize the sampling. I gotta be a little quicker here, maybe. So massive parallelization for n equals 1 that reduces to standard serial Markov chain Monte Carlo on Metropolis-Hastings. The proposal kernel is flexible, so the first guess is just to take a random step drawn from like a normal distribution, but there are smarter things that you can do. It does have improved performance to serial MH. So just a quick glance at the implementation details. So everything is C++ classes. So we have base classes, and the system moves the framework, puts it all together, and executes everything in the right order. So we can have a Markov chain Monte Carlo class that we can derive from to implement, for example, parallel Metropolis-Hastings. We have the multi-app system that will then execute sub-applications to sample, to perform the model evaluations. And then we have the decision-making, which will basically check if steps are accepted or not and report this back to the MCMC class that then takes the next step. Attached to that, we have diagnostics classes that allow you to on the fly supervise or control or diagnose the sampling process, like if using effective sample size and so on. All right, so quick case study on that. Again, TRISO. TRISO fission product release from AGR2 advanced gas reactor. So those are old experiments. We did not design those experiments, and if we had been around, we would have done things differently, as you will figure out in a couple of minutes. So those are, again, very difficult experiments. You have to take this radioactive crap out of the reactor and analyze it in hot cells and so on. So there's very few data points. 36 capsules were analyzed for the release of silver from these particles, and all under some different operating condition, different temperature, and different fluents and so on and so forth. And we want to basically look at this TRISO kernel and ask the question: can we determine what the prefactor for the diffusion and activation energy for the diffusion through the layers are? So there's a couple of parameters that we would like to infer, and so we do this inverse analysis, infer these 6 parameters. So the runs I'm going to show are 50 parallel proposals, and as we have the 36 data points here. We have 36 evaluations, model evaluations. We use 1,800 processors on our supercomputer. That's just the proposal distribution. That doesn't really matter. Okay, so if we do a simple, naive, parallel Metropolis-Hastings sampling that looks, quite frankly, horrible. I mean, these parameter distributions are wide, they're multimodal, and you kind of, if you've looked at such a graph before, you know that we're not really exploring the space very well, right? This is a very clustered random walk. Well, we do get, from these, if we put these parameter distributions in, we do get confidence bands on the predictions, and sure, they do capture the experimental data somehow, but this is not the end all. So you have to do some diagnosis when you're doing these uncertainty quantifications. So there is uncertainty in the uncertainty estimation. And yeah, for that, we look at the sampling quality using the diagnostics that we have. We have like 60-ish thousand samples that we're taking here. Acceptance rate, 12%, not great, not horrible. But if you look at the autocorrelation between the samples, they are extremely correlated, which results in like very low effective sample sizes. So if we had taken only 10-ish completely independent, statistically independent samples, we would have gotten like the same amount of convergence or quality here. So that's obviously not great. An ideal sampler is one where you kind of know the distribution that you're drawing from, and you can just do Monte Carlo, right? Randomly draw, and that has basically no autocorrelation. This is bad. So what we implemented is a so-called affine invariant differential evolution sampler. And that's a really clever method. Goes back to these guys here, where where your proposal distribution isn't simply like a normal distribution, but instead you take two previously accepted proposals or states and draw a vector between them, and now you scale that vector and you base your proposal on like a randomly scaled version of that vector. Why does that make sense? It makes sense because your likelihood distribution might not look like this, but maybe it looks like this. So when you do a random walk, you're like always running into the walls here, right? But whereas if you take a vector created from previously accepted proposals, you're much more likely to explore the very likely regions of your high probability regions of your distribution. And that makes a huge difference. I mean, I just couldn't believe it. These autocorrelation plots are a little misleading the way they are plotted, because what you're seeing here is basically every 50th sample from this parallel Monte Carlo walk, which has a bit more autocorrelation than all the other samples. So the effective sample sizes are orders of magnitude higher when you do this differential evolution. And I mean, you can just immediately see it that you're exploring the parameter space much better suddenly. And your distributions now look smoother and so on and so forth. But really still super wide. And then it kind of we realized that, are we idiots or what? I mean, this problem that we're looking at is a diffusion through like a set of layers, and you can think of it like a serial resistor problem, right? And we're measuring what comes out at one end. So if you switch resistors, right, you get the same result. So anyway, what we're currently working on is adding constraints, and we can do that very easily, where we, in this case, what we put in is we're just putting in two constraints. We're saying that one activation energy is larger than the previous energy, is larger than the previous energy, and that forces a certain amount of ordering. And then we can see that at least here in this last layer, where suddenly our distribution, which was this blue one, the yellow one is crap, the blue one was very wide, and now the red one with the constraints is suddenly quite a bit peaked. So we think we need to add a little more physics to that. We could, for example, easily get estimates for the prefactors. All right. Exascale opportunities, parallel sampling will allow us to really trivially parallelize and burn a lot of CPU hours. We can infer model parameters with uncertainties from more complex experiments if we have more computing power. So one of those projects that we're I should be currently writing a proposal on is Taylor impact tests, where you shoot like a little metal bar at a wall and then you look at how it mushrooms up, and that gives you an integrated way of checking for the high deformation rate plastic response of a material, and it would be really cool to parameterize models from those tests. To do are gradient-based methods. Those are horrible. You have to retool your software. It's expensive, and so on. All right. Okay, that's it already. Okay, so what did I show you? I showed you a little bit about. I didn't show you the rapid model development. I kind of did. So it's really easy to implement new mesoscale models in Moose. So if you ever wanna take your electronic structure insights and see if you can upscale it, I encourage you to check this out. Multiphysics coupling, effortless parallelism. If this parallel multi-scale architecture with a sub-application system where everything is in memory, you can wrap external code, so it makes us really well positioned for developing these statistical sampling methods and multi-scale methods. And yeah, we have this new stochastic tools capability with parallel MCMC, inverse and forward Bayesian inference that, yeah, we are still working on, but there's a lot there already. Okay, thanks.